This unit on solutions and molarity and solubility and just aqueous situations in general. This is one of my favorite units, and it's one of the most important conceptually. If you are planning on taking AP chemistry, this unit is absolutely unequivocally essential. And you definitely want to understand all of this as much as humanly possible. If you're planning on taking AP biology, this is also really, really, really useful, especially on the conceptual level, maybe less so on the calculations. And just for real life, I feel like there's a lot of really good, useful information here, even compared to other units. So let's kind of dive right in. I want to add, there's a big list of definitions that we're going to get through part of today. I want to kind of add one just at the top here. Aqueous. We have actually gone over this before. And you know what? I just forgot to pull out those notes. So give me 1 second to find them. So back, this is unit, whatever number it was, the reactions unit, way back from last semester, a while ago. We talked about all sorts of chemical reactions, but we also talked a little bit, we introduced the concept of states of matter and solubility. We're going to go into that in way more detail now. So far we have talked about solids and liquids and gases when we were talking about states of matter. And then of course we just did the gas law unit, which is all about gases. But we didn't really talk about aqueous, which is not exactly a state of matter, but it's really, really important. And what aqueous means is that this is a substance dissolved in water. The substance is usually a solid, but it can be a liquid or a gas. This is so important because the vast majority of chemistry we do is in the aqueous state. So knowing that things dissolve in water and what that actually looks like and its properties are insanely important. You'll remember also from this time that we talked about solubility in terms of this little solubility chart on the back of the periodic table. Keep this handy, we're definitely going to need it. So an aqueous substance is something that is dissolved in water. Dissolving means that different compounds or particles mix completely and become completely homogeneous, that you can't see the difference between them. A solubility is how much a substance will dissolve in another substance. So if something is soluble in water, it means that it dissolves in water. If it's not soluble, if it's insoluble in water, it means that it won't dissolve in that substance. Generally, we're talking about water, but sometimes we dissolve liquids, compounds, or things in other liquids or gases even. You can dissolve gases together. You can dissolve gases into water or dissolve gases into other liquids. A good example of that is, think about like paint. Paint is not dissolved in water, but it's a bunch of pigments that are dissolved in some sort of oil. Well, actually, some paints are dissolved in water, but like oil paints, for example, are pigments that are dissolved in oil. So that is a solution. It's all homogeneous. They're all mixed together. For this example, salt is soluble in water, but wax is insoluble in water. That's true. Some pigments are soluble in wax. That's how you get different colored candles. Those are some words there. If something dissolves in water, let's draw a little picture of what that might look like. So the very bottom of your notes have a lot of blank spaces, and I want you to organize this into this kind of configuration. We're going to do 5 different drawings. So I have a little bit of space here for 2 drawings, and then I've got 3 spaces for other drawings, and they're going to have 3 beakers in each of those and 2 in these. So you'll want to kind of copy that down. Today, we're going to go over these 3. The next sets of notes, we're going to go over other topics. So this first one, let's talk about what it means for something to be dissolved. So we're going to use water as our example. So imagine these beakers are both full of water. That's why I chose blue paper for this note background. If something is soluble, so this one is going to be soluble. I always spelled this wrong, but I think I did it correctly today. This one's going to be insoluble. Something that is soluble in water, all of the little particles, whatever this thing is, whether they're ions or molecules, or whatever, they are all going to be floating around the water. And each one of these is going to be surrounded by water molecules. And there's plenty of water in between. So everything is just nicely all mixed together. So when you dissolve sugar or salt into water, it looks exactly the same as normal water because it's all soluble. Okay. If something is insoluble, this does not happen. Instead of it all being mixed in, the insoluble substance will all just be sitting at the bottom and not mixing in with the water. You've seen this before if you have like sand that gets mixed up in water or like mud, you know, it kind of looks, you can kind of see it all mixed together, but eventually it all just settles down. It is insoluble. Can you tell that that is purple at the bottom? Close enough, hopefully. I tried to test these colors and I guess it didn't do it. Well, that's not terrible. Okay, anyway, that's insoluble. So one thing to keep in mind is a couple other vocab words to keep in mind with this. In this case, the water is the solvent, and the little pink dots, whatever they are the solute. So the solute is the thing that is dissolved in the solvent. Technically, it's whichever one is the bigger number. So if you have two gases together that are dissolved, so the Earth's atmosphere is made up of primarily nitrogen. So nitrogen is the solvent, and oxygen and carbon dioxide and water and all sorts of gases are dissolved in it. If we're talking about a solution like this, the solid thing that you dissolved is usually the solute, and the solvent is the liquid that it's dissolved in this particular case. Okay. Different compounds will dissolve or will be soluble or insoluble, just depending on their properties. And those properties are if the, it's all about the interactions between the particles. So the solvent or the solute has interactions with itself. Little interactions. If those interactions are less than the interaction of the solute with the solvent, in this case water, then it's going to be soluble. So that's the electrostatic attraction / IMFs. Okay. If, in this case, draw it this way so we get a little bit of ... space. If those interactions are stronger than the interactions between the water and the solute, it's going to be insoluble. So that's the force of those IMFs. So that's really the difference between them. So insoluble compounds just attract each other far more, and the water is not able to rip those bonds across or rip those interactions apart because they're just too attached to each other. So they stick together and they don't dissolve. That's pretty much the reasoning. This also accounts for polar versus non-polar solvents. So I'll show you this. This happens on the notes on the next page. We might go into this in more detail later, but there's a general rule here that polar substances will dissolve other polar substances, and non-polar substances will dissolve in non-polar solvents. It's like the kind of wax, paint, oil thing versus like water and salt and things that dissolve in water. It really just has to do with the fact that the polar substances are generally more attracted to each other than the water, or the water is attracted to kind of itself more than it is to the oil, so it doesn't really dissolve. But this general idea of like dissolves like is usually universally true. So something to keep in mind. Okay. So let's go back to, I think we went through soluble, so we talked about solute and solvent. Now we need to talk about concentration. So concentration is the amount of solute in a volume of solvent. It's usually measured in molarity, which is moles per liter, or M. We're going to talk a lot more about molarity later and how to calculate it. There's a lot of other ways to measure concentration, like grams per liter or parts per million, lots of other ways, but that is a whole nother thing. I'll show you an example here. Let's draw two different volumes. Let's do like half of a liter, and let's do 1 full liter. I think that's kind of fun. Okay, so this first one is going to be an example of a very concentrated solution. Okay, so these are two beakers with different volumes. You can assume they're also full of water. This one is half a liter, and it seems to have about 20 little dots. This is 1 liter, and it also has 20 dots. So this one, we would say that this one is concentrated, and this one is dilute. And whether something is concentrated and dilute has really nothing to do with the volume or the amount of moles or amount of something in it. It's the ratio of the two. So this one has like 20 for every 0.5 liters. This one has 20 for every liter. So the concentration is really different. We'll get more into that later, but this one is definitely more concentrated. Again, volume, it's a combination of the volume and the amount of stuff dissolved in it. You can kind of tell just by looking that one looks like all the particles are much more packed together, and this one, they're a little bit more distributed. So concentration versus dilutedness. Just for fun, we can calculate it, but molarity is moles per liter. So in this case, if each of these dots represents 1 mole, we have 20 moles in half of a liter. And so that's going to be 40 molarity is our concentration, and my lights just went out, of course. Whereas the other is going to be 20 moles in 1 liter, which is 20 molar. So obviously this one is twice as concentrated as this one. Again, it's that combination of volume and stuff, moles or grams or whatever of stuff in it. It's actually moles, but sometimes grams count too. Okay, so that's kind of concentration. Definitely concentrated versus dilute is something to be aware of. All right. The next thing I want to talk about is we're going to come back to saturation and electrolytes in the next 2 videos. We're going to talk a little bit about precipitation. This is a type of reaction where you have chemicals that 2 solutions that are soluble, two chemicals that are soluble, but one of the products is not, and it precipitates or falls out of solution. Kind of like rain. Rain is precipitation. It's when like the water that's dissolved in the sky like falls out of the solution and is no longer dissolved in the sky. That is a really weird way to think about it, but it's actually kind of true. Like weird. Anyway, the precipitate is the insoluble compound that actually falls out of the solution. Precipitate is interesting, this word, because it can be a noun or a verb. If it precipitates or precipitate, depending how you pronounce it. Precipitate. Weird. Anyway, okay, so let's do a quick example of that. So let's just say we've got 2 solutions here. Let's just say we've got half of a liter of each. And one of them is going to be, let's say, let me see, I might need another color here. What would be a good, maybe the red, that should work. Maybe something else. What would not, maybe is green gonna look okay? Yeah, green looks great. Okay. So let's say we've got some barium, barium chloride that's dissolved in one. So I'm going to draw a picture of that in just a moment. And then I've got some sodium sulfate in another. Okay. So the first thing we have to think about when we have chemical compounds like this is, will these dissolve in water? And we can go back to our little solubility chart here and find out that chlorides usually dissolve in water with a few exceptions, but barium is not one of them. And sulfates usually dissolve in water with a few exceptions, but sodium is not one of them. So these, in fact, both will dissolve. So I would say that these are aqueous. Okay. All right, so these two are going to react, and they are going to form some products. Okay, our products are going to be sodium chloride. Oops, sodium. We've got all these colors. Let's use them. Chloride, which is going to be a thing, and then of course barium sulfate. Should leave these markers open. I'm going to need them a lot. Okay, so the question here now is, we've got these products. Are they soluble? So let's go back. Chlorine and sodium, definitely very soluble. We know that sodium chloride dissolves very readily. There's actually going to be two of them to balance the equation. But barium sulfate, let's find out. Sulfates are usually soluble, except, barium is an exception. That means that barium is not soluble, and it's going to be a solid in this reaction. So this is an example of a precipitation reaction. So here's what's going to happen. The barium and the chlorine, 1, 2, 3, 4, 5, 6. I'm going to draw the right numbers of everything too, just to be very precise. 1, 2, 3. So the barium chloride, and let's do 1, 2, 3, 4, 6. And silver sulfate would look like this. There's the barium chloride and the silver sulfate. They're all dissolved. Everything's great. When we pour these two together, a couple of things are going to happen. First of all, the volume is going to double. We're going to be, because we're mixing them together, we're going to be at 1 liter instead of 0.5. The chlorine and the sodium are just going to still be around. Six. 1, 2, 3, 4, 5, 6, because they're going to dissolve. But the bell's ringing. Hold on a second. The barium and the sulfate are not going to dissolve. They're going to precipitate out at the bottom. So there's that. Okay. That was pretty much all the notes. That's an important thing to talk about for later, but let's just talk about the unit packet for a minute here. Your packet pages are going to be pages 1 and 3. Let me give you a quick example of both of these. For this unit, the page 10 is a bit of a review. It's just if something is soluble or not. So for example, lead carbonate. Carbonate is here. It looks like it's usually insoluble, and lead is not an exception. So this is going to be insoluble. Insoluble versus soluble. Ammonium hydroxide, for example, is definitely soluble. Hydroxides tend to be insoluble, but ammonium is an exception. For these ones, you're going to need to try to predict the two products if they're mixed. So for example, if potassium bromide reacts with silver nitrate, the potassium and the silver are going to switch places. So you're going to end up with KNO3, and you're also going to end up with silver bromide. And the question is, will either of these precipitate out? So we got to double check. NO3, pretty soluble. AgBr, Br will precipitate out with silver. So that one is solid. That one is aqueous. Okay, that's what you're going to do for the rest of those, kind of combining the two. Okay, Last thing, for these ones, I just came up with a couple little examples. This is separating out the ions to really just kind of conceptualize what it means for something to dissolve. So silver, like we just said before, ammonium hydroxide is soluble. Anything with sodium in it is pretty much going to be soluble as well. So when they dissolve, you're going to split it up into the two ions that are both going to be aqueous. So that's that. With the sodium, there's going to be two of them because that two here, they're both going to split off separately. And the carbonate is going to be a 2-, and that's also aqueous. Okay. So we can go over some more of these in class, but at least that will get you started. And we'll go from there. So good luck with all that. I hope that these visuals have helped you to understand what solutions are, and we will continue to practice. If you don't know, let me know. It's going to be a great unit. Hooray. Yay.